Today's speaker is Alistair Miller, and his title you can see there, Correspondences, Homology, and K-Theory for étale groupoids. Please, Alistair, go ahead.
All right, thanks. The sort of motivation for this talk is really to try and understand K-theory for étale groupoid C-star algebras. So this is the picture I want to think about. There's multiple different angles you can come at this picture from, because loads of things feed into étale groupoids. You can build, that in general, they're just sort of some kind of framework for describing discrete time topological dynamics, I guess, is the way I'd want to summarize it. So it means they're incredibly versatile and you can find them from lots of different sources. And then what C-star algebraists like to do is they like to build C-star algebras out of these. And that turns out to be a good idea, partially because you can then build K-theory groups, and these tell you lots of information about the C-star algebras and about the groupoids. Also because this actually gives us a lot of C-star algebras. Like, these are incredibly versatile as C-star algebras as well. So for example, you have the result that every classifiable C-star algebra can be written as a twisted groupoid C-star algebra. So I think this is sort of a picture that even just, pure C-star algebraists would be interested in this sort of thing, but also people who want to sort of use C-star algebras as tools to study other things, I think. So that's a sort of overall motivation. And the problem is that because these things are so versatile and so useful, it means that it's going to be basically impossible to say very general statements about this. We're not going to be able to compute the K-theory of étale groupoid C-star algebras in general. Even for group C-star algebras, this is very, very difficult. So one of the things that people have done to try to get a bit more of a handle on the K-theory of certain groupoid C-star algebras is to try and compare it to something called homology, called groupoid homology. So people look at ample groupoids, which are étale groupoids where the space involved is totally disconnected, so it's zero-dimensional. It's the sort of easiest possible in the geometric direction. And then it's much easier to talk about sort of algebraic things with respect to the ample groupoids. And then groupoid homology becomes quite natural to study as a generalization of group homology. And it turns out that there's going to be some connections between groupoid homology and the K-theory of the C-star algebra. And I'll get a bit more into that later. But what I want to think about today is how can I sort of upgrade this picture so that it's functorial. So I want to think of morphisms of groupoids, which are going to just work nicely with this picture. And so, for example, give us morphisms of C-star algebras, give us morphisms of the abelian groups on the right-hand side. And then the other part of the question is, how can these morphisms actually help us? Like, I don't want to just build morphisms for morphism's sake. I want to do it to do something, to get some actual concrete results at the end. So here's a sort of teaser of that kind of result. And it says, so this is the kind of C-star algebras whose K-theory I can now compute using the techniques that I'll tell you about today. So we start off with an inverse semigroup, which is sort of a quick definition is that it is, definition is probably the wrong word, but as quick description is that inverse semigroups are the algebraic structures of partial symmetries, whereas, compared to groups being algebraic structures of symmetries. So particularly they have all these groups living inside them, so-called maximal subgroups, for every idempotent. And it turns out there's a very natural C-star algebra you can associate to one of these guys. And it turns out if you want to understand the K-theory of this left regular C-star algebra, it will just split into this sort of orbit stabilizer formula, where now we've reduced the problem to understanding the orbits of the idempotents within this thing, and the K-theories of the C-star algebras of all of these maximal subgroups. So just to sort of like, okay, what's the first interesting inverse semigroup? Maybe it's not the first interesting one, but it's definitely an interesting one. It's the polycyclic inverse semigroup, which is related to the Kunz algebras. And if you take this inverse semigroup, this formula here will tell you that the Kunz-Toeplitz algebra has the K-theory of the complex numbers. So that's the sort of thing that this is recovering. That's the kind of statement this is making. But we're able to make it for more general inverse semigroups. All right. So yeah, now I'm going to talk a bit about groupoids. But maybe first, now's a good time for any questions on this or this. So please do ask.
Well, I have one question. So one goodness of this version for C-star algebras is that one knows that certain groupoids do satisfy the bound cone projection, right?
What? Sorry, one weakness or one?
One knows that certain groupoids satisfy the bound cone projection, so you can apply the three of them, right?
Yes. So there's a famous
in the
result.
purely algebraic context, you have there is a similar theorem for the plain groupoid algebra, the Steinberg algebra. But the point is that, I mean, at least I don't know any groupoid, I mean, that satisfies the right conjecture from the start.
Yeah.
That's, yeah. Okay.
Yeah, and actually it's worth mentioning that you can remove the word satisfies a bound cone conjecture here and replace the K-theory of the C-star algebra with what would be the left-hand side of the assembly map. So everything works just for working with the topological K-theory with the groupoids involved. Yeah. All right, cool.
Yep.
So, right, now I'm going to talk to you about the morphisms of groupoids that I want to consider. And basically, you can see all these dots up here. What I'm going to try and do is just kind of bombard you with examples of these guys and different classes of examples of these correspondences. Basically, just to try to convince you that these are a good notion of morphism of groupoids or of étale groupoids. And yeah, I think these should be seeing more use in general. So yeah, first we'll start off by looking at the K-theory picture. So this is we really want to make this functorial, okay? So we send a groupoid to the C-star algebra to the K-theory, and I think the problem of making the groupoid C-star algebra construction functorial is a bit subtle, because the very naive thing, which is to take the structure preserving maps, the sort of continuous homomorphisms, I'll call them, and see if you can build something on the level of the C-star algebras. But the problem is this is completely doomed to fail, because if you just look at groups or at spaces, then they are both functorial, at least if you make enough assumptions on them. But broadly speaking, they're functorial just in opposite directions. So the group C-star algebra construction is covariant, and the space C-star algebra construction is contravariant with respect to the structure preserving maps. So it's hopeless. We can't hope to find a good notion of morphism of C-star algebras here from general continuous homomorphisms of groupoids. But a very different kind of morphism of groupoid is seen everywhere. And I think if you take any paper that has to do with the K-theory of groupoid C-star algebras, you probably see them invoke Morita equivalence of groupoids at least like 5 times. So this is everywhere, and the point is we want our morphisms to encompass these Morita equivalences. And so they give you the same K-theory, so it's really it's a good notion of equivalence to work up to if you just care about the K-theory. So in another direction, there are these things called Zakrzewski morphisms, which are also known as actors and as algebraic morphisms. I think what's happening is that they seem to be a very natural notion of morphism for groupoids, but they're not completely obvious. So lots of people rediscover them in different contexts. And so they've probably got many more names across maths. But I know at least 3. And what these do, at least on the C-star level, is they sort of model star homomorphisms quite well. And those will obviously give you maps in K-theory. So étale correspondences, really, they sort of combine these last 2 things and more. And on the C-star level, they give you something called a C-star correspondence. And this is also going to be able to give you homomorphism at the level of K-theory groups. And the word proper appearing here, it's like when you want a continuous map of spaces to be proper in order for you to be able to get an actual star homomorphism at the level of the C-star algebras. Otherwise, you just get something involving the multiplier algebra, and that's not good enough to get you something in K-theory. So point is we get Zakrzewski morphisms, we get Morita equivalences, but it turns out we can actually also get a lot of homomorphisms. We just have to ask this extra condition that they're étale, meaning that the homomorphism is itself a local homomorphism between the groupoids. So particularly get open inclusions and other examples. So actually the example that got me interested in all of this doesn't fit into any one of these categories, but anything can be sort of abstractly written as the composition of Morita equivalences, Zakrzewski morphisms, and open inclusions. So I've sort of given you everything already, but maybe things appear more naturally as just a correspondence in itself. All right. So I'm just going to quickly review what a groupoid is and how I think about groupoids, maybe more importantly. So I think of the elements of a groupoid as arrows, which I draw on something called its unit space. So X, Y, Z, they're elements of the unit space. G and H, they're arrows. Because they're lined up nicely, I can compose them. I have other group-like axioms. So I have identities, that's why it's called the unit space. And I have inverses. And if you haven't seen groupoids before, I'd encourage you to just think about these 2 examples. So with a group action, hopefully you already have a picture of arrows on a space, and really those arrows give you the groupoid. And that's what this notation here means. Oh, here. On the other hand, if you've got an equivalence relation on a space, you can draw an arrow if 2 points are related. And this gives you a groupoid, thanks to the equivalence relation axioms. Usually I'll use an R to denote that it's an equivalence relation. So yeah, these are sort of two ends of the groupoid spectrum in some sense, in a different way so obviously spaces with only trivial arrows are also groupoids, and groups which only have one unit are groupoids. And I work with étale groupoids. So this means I want the space to be topological, but I don't want to consider any more. Like I want to only have to think about the topology of the space, really. So the point is that the topology of the whole groupoid is inherited from the topology of the space through the range or equivalent of the source map. And it means that every arrow fits inside what's called a bisection. So rather than having to work with these spindly little arrows G, I can fit everything inside a big fat arrow called a bisection, and that's going to move some neighborhood of X to some neighborhood of Y. And I can think about the dynamics that way. So just like groups, groupoids can act in spaces. It's just a little bit more fiddly. And fundamentally, we still want to be writing things like g.x, where g is in your groupoid and x is in your space. We just have to say that they're compatible somehow. So we've got the trivial action where an arrow takes its source to its range. Left multiplication still works as an action, and you just have them act whenever it makes sense. In general, this is going to be controlled by something called an anchor map. So it means that if you want your element G to act on your point X, you need that X to be mapped down to the source of G under the anchor map. And then you better make sure that G.X maps down to the range of G, like that. And in every other way, it's just like group actions, so there's no point going over those. What this means is that I've just accidentally defined what it means to be an action of a space, because spaces are groupoids. And it turns out what I mean by that is I just have a map over the space Y that I'm acting with. So an action of a space means that you fiber over that space in this context. All right. So I did this because now I can give you the definition of a groupoid correspondence or an étale correspondence. So I want to think of, so an étale correspondence is a bispace. So it's got an action on the left of G and on the right of H. But I want to think of this as like having a direction. So it's a morphism that goes from G to H. So because these are groupoid actions, they come with these anchor maps on the right. I've called them rho and sigma because rho is for range, sigma is for source. And we're going to have a couple of conditions. So first of all, it wants to actually be a bispace, i.e. the actions should commute whenever these things make sense. And we want the right action to have lots of nice properties. So this is where we lose the symmetry in the definition. So the right action has to be super nice. If you know what free and proper means for a group action, this is extremely similar. And we have this final condition, which is the étale bit. And it means that the right anchor map, the source map, is étale. And a bit of terminology is that we call this action étale in this case. The word étale will always mean that something is a local homeomorphism. It might just vary what that thing actually is. But in my head, étale is just a synonym for local homomorphism. And yeah, it means slack in French. But that doesn't help me. It helps some people. Yeah, there we are. And just like you can ask for a continuous map of spaces to be proper, we can ask for a correspondence to be proper. And that's if this map here I've called row bar is proper. And what row bar is it's just the range map is going to be invariant under the right action of H. So it descends to a map of the quotient, the orbit space, and we can just ask for this to be proper. So this is the sort of thing that's going to actually get us things on the level of K-theory, etc. All right, so I've got the definition there still, and I want to talk about equivalences. So Morita equivalences. Because the point is that Morita equivalences are like if you try to symmetrize everything and make everything as, everything have the most isomorphic flavor they can. So we have this sort of setup with a bispace, and now we want both actions to be super, super nice. And we want these induced maps here to be homomorphisms rather than just proper. So it's stronger than being proper, and it's stronger than the sort of the reverse thing being proper. It's as nice as we could get it. And in fact, the Morita equivalences are going to turn out to be exactly the invertible correspondences. So there is a composition of correspondences, which I'm not going to tell you about. And with that composition, they become a category, well, two category, but category, and then the Morita equivalences are the invertible ones. Good. So some examples of Morita equivalences. I think this is the sort of, this is the most basic example, and this is the analog of the C-star algebra Morita equivalence between the m by m matrices and the n by n matrices. And so we can see here that this equivalence relation on 3 points and the equivalence relation on 2 points, they both act on the 6-point grid. This one sort of moving things horizontally, and this one on the right will move things vertically. And you can check that those actions commute, and they're as nice as they could possibly be. Any groupoid acts on itself by left and right multiplication. This is sort of the identity correspondence. And so it is definitely an equivalence. If you take any groupoid and let it act on itself by left multiplication, you get a new groupoid, action groupoid, and this is going to be Morita equivalent to the unit space of the groupoid, and the bispace is the groupoid itself. This is quite a nice example, which is that if you've got surjective local homomorphism between spaces, you get an equivalence relation on the first space by, okay, are these the same in the second space? And then you build an equivalence relation out of that is equivalent to the second space, just by acting on first space y. And here's this sort of classical example, which is if you've got a free and proper group or groupoid action, then you'll get an equivalence between the orbit space and the action groupoid. Okay, cool. So the next sort of category of examples I want to talk about is these étale homomorphisms. So if we had a group homomorphism, then we know we can build a C-star algebra homomorphism out of those guys. And we can actually build a correspondence with the groups, because the first group will act upon the second group through the homomorphism, and that's all we need. We tried to do this for groupoid homomorphisms. Turns out we can modify things very slightly and construct this bispace, which I don't want you to think about the details for, particularly. I don't think that's important. The point is just that we can do it. But if you do this, you'll notice that this is only going to become an étale correspondence if the homomorphism itself was a local homeomorphism. So this is where this condition is coming in, but if it is, we do get an étale correspondence. So we cover things like open inclusions very easily, but also this example from the previous slide fits into this context as well. So if you have this surjective, or it doesn't even have to be surjective now, but if you have this local homeomorphism, then the map going from the equivalence relation to the second space will be an étale homomorphism, and it will give you the same correspondence as the one I described on the previous slide. All right. So we've got Morita equivalences, we've got étale homomorphisms. Now I'm going to talk about the Zakrzewski morphisms. So this is an action of the first groupoid on the second one that's compatible with the right multiplication. And one reason these are great is because if you restrict to just looking at groups, or if you restrict to just looking at spaces, these give you sort of exactly the most natural maps, exactly the structure preserving maps. But now they're in the opposite directions. So this fixes our problem from before, that the construction of the groupoid C-star algebra kind of couldn't be made functorial with respect to the structure preserving maps. Because these now deal with the group bit and the space bit in sort of a compatible way. And indeed, we can get a star homomorphism from these guys. In general, it's just going to be to the multiplier algebra, but if you have properness, it will go to the C-star algebra itself. So this covers open groupoids, which contain the whole unit space. If you ever have an action, you can get one of these guys. You just write down, there's nothing deep here, you just write down the obvious thing. And I think the more interesting example is this one, where if you have a homomorphism in the opposite direction, which has a bunch of properties, so it's proper, it's surjective, and it has this sort of technical looking condition of fiberwise bijectivity, turns out you can, from that data, you can actually construct an action of the second groupoid G on the first one H. And this is the kind of morphism that sort of appears, well, these things appear in Shinli's paper where he constructs groupoid models for every classifiable C-star algebra. So these kinds of proper surjective homomorphisms are very important in that construction. And so we can see now that they are, we can interpret them as Zakrzewski morphisms. And it sort of makes sense if you're thinking about star homomorphisms of C-star algebras, you might want to consider these in the groupoid level. Groupoid model, right. Good question. So if I use the word groupoid model, I probably mean that there's a construction of something from a groupoid, probably a C-star algebra. A groupoid model for that C-star algebra is then a groupoid whose C-star algebra is your original C-star algebra. So if I'm thinking about C-star algebras and I want to study them using groupoids, I'll often use the word groupoid model to be like, okay, now I can work in groupoid land. This groupoid. Thanks. So this was Zakrzewski morphisms. Let's get a bit easier again. So what does a correspondence of sort of trivial groupoids, i.e. spaces, mean? It just means that we've got two continuous maps and one of them's a local homomorphism. So whenever you have an open cover, you get one of these guys. Because if you take your bispace to be the disjoint union of all of the opens in your cover, this will have this nice local homomorphisms onto the space, and then you'll get this map to the index set, which, is just a discrete space. And you can properness here is just saying that all of these things are compact. So, this is reasonable if you're working in totally disconnected spaces. And this sort of builds me onto this example that is really, for me, the motivating example. This is why I'm doing all of this. So, yeah, I'll just talk a little bit about inverse semigroups first. And for me, inverse semigroups always have zero, and you always respect the zero. It's mostly just a matter of convention, but that's the way I do it. And what it is, as I said, it's a semigroup of partial symmetries. So, for example, partial homeomorphisms on a space, which means that you have two open subsets and a homomorphism between them. Or, for example, you can view an open bisection in a groupoid as like a partial symmetry that's sort of within that groupoid. Here I'm thinking about as this sort of like big fat arrow U that I draw on the groupoid. So if I look at, the polycyclic inverse semigroup is, I believe, the star semigroup generated by the Kunz isometries. Of course, it also has a very simple presentation in the inverse semigroup world. And I'm not sure inverse semigroup theorists would be happy with me defining it this way, but this is an NCG seminar, so I think this is justified. So, right. And what's this correspondence that I'm going to build? Oh yeah, and this picture, by the way, is just the picture I always like to have from talking about inverse semigroups, because the point of composition is that the domain and the range might not match up. So you just have to restrict to the sort of intersection where everything makes sense. And that's what you're seeing with the red zones here. Hope that makes sense. So in an inverse semigroup, you have the special subset of idempotents, which we think of as like the domains and the ranges of our partial symmetries. I always use letter E for that. And now I'm going to build two groupoids. The first one is a discrete groupoid called the underlying groupoid, which is just the elements of S, but now I declare the range and source of an element to be its range and source projection, i.e. its sort of domain and range in this partial symmetry point of view. And this gives us a groupoid structure, because now if the domain and range match up, then you can just compose them and you get sort of actual complete composition, not just this partial composition. And the other groupoid I'm not going to describe completely. It's called the universal groupoid of the inverse semigroup. And this has more interesting topology. It's an ample groupoid, and its unit space is this thing called the filter or the character space. So the idempotents are closed under multiplication because it's just like intersection of domains, for example. So we can ask for a character on E, and we look at the character space. There's also an order theoretic characterization of what's going on here, and that's why the word filter appears. So sometimes I might slip up and call it a filter space. Don't know if that's slipping up. That's why I've got the word there, anyway. And this has a nice totally disconnected topology. So for every non-zero idempotent E, I have a compact open of all of the filters which contain my idempotent characters which evaluate to 1. And I've just given you an open cover. So I have a correspondence on the left here. So I've got a correspondence on the space level between these groupoids. which is just taking this open cover and I take the disjoint union. But I can actually sort of upgrade this into a correspondence between these two groupoids. And here this notation means it's all of the groupoid elements in the universal groupoid whose range lands in this compact open UE. I don't care about what happens to the source, but I just want the range to land in there. So I build a correspondence, and it turns out this is a nice proper étale correspondence. And it's proper exactly because each of these open sets is compact. Right, so just going to summarize all of these things. So this is I promise, the end of the bombardment of all of these different correspondences. So we cover Morita equivalences, use étale homomorphisms, Zakajewski morphisms, which could be from actions, they could be from these homomorphisms, in backwards homomorphisms, really. We can get topological correspondences, such as correspondences bases from open covers. And this one I'm interested in, this inverse semigroup example. Okay. And yeah, now's a good time for any questions, if people have any.
This correspondence, the last one you talked about, which is here the right, the last before the last, the previous to the last. So if, so say, I mean, if you look at the algebra of the discrete groupoid, so as a vector space, it's the same as the groupoid algebra, only that as the semigroup algebra, which is the groupoid, the other groupoid algebra.
Exactly.
The product is 0 unless the domain and the range match up exactly.
Like, yes.
Now, so there is no algebra map from this discrete guy to the other guy. However, you can map the first one to the matrices on the other. So is this map to the matrices or to the compact operators or whatever, does it represent the same thing in, say, KK as your correspondence? That's
I think that's exactly it. So correspondences on the level of C-star algebras are like representations of the first algebra on a Hilbert module over the other one. So yeah, if you map into say the stabilization or something, that's exactly what's happening here. And that's, I think this is it's all part of the same thing. Yes.
Okay.
Cool. All right. So now I'm going to talk a bit about the homology and the K theory and how they're linked. So just to remind you of this picture that I started off with. We have this diagram where we want to study groupoid homology of ample groupoids and K theory of groupoid C-star algebras. And I now have some morphisms that I want to make work with this diagram. So that's what we're going to try and do. So on the C-star level, this was done sort of in the non-étale setting by Holkar, and then sort of in the étale setting and with all of the sort of possible assumptions removed by these three authors. And they say that you induce something called a C-star correspondence at the C-star level. which is exactly the sort of thing where you don't get a map of the algebras, but you do get something like a map after you take matrix algebras. And so if this thing's proper, you get a map in K3, because we know that these guys work well with respect to K3. So that's the top layer of the diagram sorted, so that's good. And I've got this slide just in case we want to talk about what ample groupoid homology is. I'm not sure I have time to go through it properly. The point is, it's all about this thing called the groupoid ring, or maybe is in the same way that every C-star algebra has an approximate unit, and you can still do a lot of things with that. So then you just work with module categories of this ring, and you can define tensor products and groupoid homology as a Tor functor. So if you know anything about this, then this is great. If you don't know these things, I've probably not helped you much with this slide. Just know perhaps that you can write down a very concrete chain complex in terms of the groupoid, where these guys are the composable n tuples of arrows, so sort of finite paths of arrows, or length n paths of arrows. That has a nice topology.
Just to be fastidious,
yeah.
The superscript on Tor, you want it to be Z of G, right?
Right. Yeah. G here is short for Z of G. In the same way that this G here is short for Z of G, and this G is short for Z of G. Yes. Exactly. And if we want to be very fastidious, I probably shouldn't have written the same N here twice. But that ship sailed. So then what I do is I show that these proper étale correspondences give you maps in groupoid homology. Because with this picture, it's a very natural thing to do, because you can, from what is a bispace, given that G spaces give you G modules, then bispaces give you bimodules. So you get functors between the module categories, and that's how this all works. And then you can very easily see that a Morita equivalence, for example, is going to give you an equivalence between the module categories, which is what you'd hope given the name Morita equivalence. So as an example, when you do this to this particular correspondence that I'm working with, it's quite elementary to see that you actually do get an isomorphism in homology. I mean, you don't need all of this machinery to construct this isomorphism homology, but what's interesting for me is that you actually can realize this as something that, you can fit this into my theorem here. This is actually induced by some correspondence. So we can see it on a more sort of synthetic level as well. So this gives you a sort of homology computation of the universal groupoid. Because this discrete groupoid here will just break down into all of the maximal subgroups up to Morita equivalence. And so you've reduced your problem to a group homology problem, and there's lots of tools in group homology that exist and you can use, and there's lots of work, and it's much more classical. So yeah, we can use these sorts of ideas to help us compute homology. Actually, yeah, Ben here in the audience, Ben Steinberg, has been throwing some ideas at me about how you can do this to help to compute some groupoid homologies of some interesting groupoids. So this seems like, you know, you really can do things with this, which is great. Yeah, what's next? Right. So what has groupoid homology got to do with K-theory? So there's this very simple relationship that sometimes holds, which is the K-theory is just the direct sum over all of the homology groups of the same parity. And for certain groupoids, this was phrased as a conjecture because there were lots of examples where it held. So it definitely doesn't work just for groups because sort of there's very easy examples with groups where it fails, particularly if there's any torsion or anything in the group, then you shouldn't expect this. And so the idea was to try to get rid of the group case by putting topologically free as one of your conditions, I think. And so many of these examples coming from topological dynamics, Matsui, like he introduced this idea and he proved it for a lot of really nice examples. So we have lots of positive results, but there are counterexamples. So Eduardo Scaparo, he constructed this counterexample coming from an odometer. And I guess, you know, what you can say is happening is that he's got torsion in the isotropy. And this really breaks everything and makes torsion is going to basically make the homology not vanish kind of infinitely often. And this is just going to be very bad in general. So really what this is telling us is that we shouldn't be asking this question if we do have torsion in the isotropy. The question should be modified somehow.
Sorry, is there a Chan character from the left to the right? And you're asking that it be an iso or that's the
Yeah,
map?
so I don't think anyone's constructed a Chern character. Yeah, so there's this other problem here that it's, as it's stated, it's just like an abstract isomorphism. But you'd sort of hope that there are some natural maps in some direction and then asking, okay, do these give us an isomorphism? And people have constructed maps. I think there's a very nice map from H0 to K0. And people have constructed a map from H1 to K1. But I think beyond that, we don't have much that is satisfying. I'll explain a little bit more about what's really going on very soon. But no, I don't think anyone's done a Chern character yet. But it's sort of, a Chern character would be plausible with torsion-free isotropy, I think. So even if you assume the groupoids are principal, this is still too much to expect. It's basically too simple a relationship to expect between these groups. So in high dimensions, this is going to break down. So Robin Dealey has this example, sort of transporting some ideas from more classical geometry into dynamics. And this, he had an example in 9 dimensions, which works. And then his student, Rachel Chaser, she made a 4-dimensional version of that still gives you a counterexample. And so here, the point is that 4 dimensions is too high for this simple relationship to hold. So we sort of think of this thing as like a low-dimensional phenomenon. And Valerio Prietti and Makoto Yamashita, they actually prove it in a sort of low-dimensional setting, where you have the homology vanishing for dimensions 3 and above, H2 free abelian, and again, this torsion-free isotropy thing is sort of crucial. Yeah. They prove it by sort of maybe shedding a bit more light on what I would say is really going on. What is the actual relationship between these guys? it's a spectral sequence. So what do they do? So if you have this torsion-free isotropy, and you satisfy the Bank-Kohn conjecture, and really, yeah, let's just, so if you have this, then you have a spectral sequence that converges to the K-theory, and the second page is given by the groupoid homology. And really what's going on is this is always converging to the topological K-theory, which is at the left-hand side of the Bank-Kohn assembly map. So thanks to this other paper of Valerio and Christian Benecke. So then if you assume the Bank-Kohn conjecture, then you get this. And thanks to two, we know the Bank-Kohn conjecture for example, amenable groups, but more generally, groupoids, even more generally groupoids, which have their Hoyle property. This is really quite a wide collection, quite a general class. We don't know of any counterexamples for exact groupoids. So yeah, it's really quite a large class. Right. And so the point is that in low dimensions, the spectral sequence sort of says that this thing is a direct sum of these guys on the left. But in general, the way, and it always says that the K-theory groups are somehow built out of the homology groups. But it's just going to be more complicated than a direct sum. Like how not every short exact sequence splits. I just think of a spectral sequence as like a big, complicated, short exact sequence. So, you know, the middle thing is built out of the things on the sides, but not necessarily in a very easy way. All right. So now we know the relationship between these guys. It's a spectral sequence. And my main result is going to be that this is functorial. So the spectral sequence and its convergence are functorial. And why do I want this? It tells me that if what's happening at the second page is an isomorphism, then I'm going to get an isomorphism of the target groups, of the things I converge to. So this is sort of in analogy with the short exact sequence idea. If you have a map of short exact sequences, which is an isomorphism on either side, is going to be an isomorphism in the middle. And it's exactly the same kind of thing, but times 1,000 that happens in a map of spectral sequences. So this is what's allowing us to sort of, even though we can't, so if we knew we got an isomorphism in homology and we knew the HK conjecture held, then obviously we'd have an isomorphism in K3. But this is saying that even though we can't expect the HK property to hold for many groupoids, we can still make use of this link between homology and K-theory and deduce something about isomorphism of K-theory groups from isomorphism of homology groups. So that's the point here. And indeed, sometimes it's easier to verify that you get an isomorphism in homology. So this is, yeah, go on.
So a question. So is the proof that of the functoriality, does it have to do with lifting this omega to a map between these resolutions? I mean,
yes. Yeah, so the construction of this spectral sequence takes place in this Meyer-Nest framework of homological algebra in triangulated categories. In particular, the triangulated category you use is KKG. So first you have to lift omega to a map at the level of KKG. What happens over here on the second page is you have these resolutions, these derived functors on this level. And so you have to make all that work with respect to You have to sort of lift omega to something that's happening over there. Basically, the point is at every stage you have to lift omega to something with what's going on.
So you mean the resolutions, these independent resolutions give you resolutions in the Meyer nest sense?
Oh, no, sorry, no. The independent resolutions is something else.
No, I was thinking of independent resolutions. Sorry.
Yeah, no. Yeah, I was sort of curious about the relationship there, but I'm not sure about how that works.
Because you do get a spectral sequence using these independent resolutions.
Right, yeah. I sort of expected that spectral sequence should be related, but I would like to think about that sort of thing more and see what the connection is there. Yeah. So this basically gives us, because we build this because we know that this map on the level of this inverse semigroup correspondence gives you an isomorphism in homology. This result then tells you get an isomorphism in K theory. So this is the result I kind of mentioned at the beginning. And the proof is just exactly what I described. I guess the point is that this C star algebra here is the groupoid C star algebra of the universal groupoid. So what was this sort of, where did this idea, why look at this? Where does it come from? What's been done before? This is, so there's something with basically the same statement, but for a much more restricted class of inverse semigroups, which in Lie. And the sort of key assumption we removed is that there is some group, gamma in this case, which sort of governs the dynamics of S. So if you do have this group gamma that governs the dynamics, then you can do everything in KKG and it's all much simpler. But without that, you have to sort of look at some groupoid methods. And that's the point. But it gets a lot more complicated because you can no longer govern everything with one groupoid. So that's why you have to look at morphisms between two groupoids, like a groupoid correspondence. Yeah, and maybe I'll just I'll give you, if I've got a minute. Yeah. So then an example of what kind of C star algebras can you write as these inverse semigroup C star algebras? You start off with something called a left countertesimal category. So either think about like category of finite paths in a directed graph where the composition is concatenation. Or you can think about a category with one object, so it's a monoid. And the singly aligned bit is basically telling you that you have either no common multiples or a least common multiple. So it's called a right LCM monoid. And when you have this, then you can get an inverse semigroup just by thinking about the action of the category on itself. You get a bunch of partial bijections generated that way. So to get this polycyclic one, you just start off with a free monoid. You get the same algebras, and this underlying groupoid here can be described in terms of the invertible arrows in your category. So the description then says that the K-theory of this guy is just the K-theory of the groupoid of all of its invertible elements. So yeah, that's all I wanted to talk about. So thanks very much for having me.
Thank you very much, Ali, for your very nice, interesting talk. I have several questions, but maybe the audience has some other questions before I start firing mine.
I have one question if that's possible to ask.
Yeah, yeah.
Please go ahead.
By the way, very nice talk. It was very clear and very helpful for me. I'm just wondering, this functoriality you have, is there some sort of two categorical version as well? Like you have a morphism between the two correspondences. Does that tell you, can that be somehow leveraged to then say something about the spectral sequences having some morphisms, or something like make a long exact sequence out of the K theory or something? I'm just wondering if you have, because I suspect that there are interesting situations where you have these étale congruent correspondences and a morphism, and you may even get that these both correspondences give isomorphisms on the homology, and then one might want to say something about, does this two-morphism give you something at the level of K theory that you could look at?
Yes, good question. I don't know what the sort of the right two morphisms would be to consider, but yeah, maybe there's something there. Because yeah, these correspondences are very naturally two categorical, which I've sort of suppressed in all of this. And for my applications, I can just consider the sort of collapsed one category where you consider really the isomorphism classes of correspondences. So yeah, I don't know. There could be something there in terms of what happens if you really think two categorically. Yeah, good question.
Yeah, yeah. Maybe one can sort of get between the homology some sort of, long exact sequence or something, and maybe that has something goes over to the K theory world. I don't know. It just seems like I can imagine situations where this kind of, where the correspondences naturally have a map between them, and maybe it says something.
Yeah. Yeah, no, that's interesting. Yeah, cool.
Okay.
I have
So,
a
yeah,
question
you
slash
are saying,
comment.
go ahead.
So in the case where we have a group, do we even then have a churn character from topological K theory to periodify groupoid homology?
You don't you? I mean, as in the algebraic, sorry to interrupt. The
Yeah.
question was not for me, but so I mean, the group homology is a direct summand of Cauchy homology of the group of the of the group
Yeah.
algebra, and actually you have a direct summand at the level of cyclic modules.
Mhm.
You can build a cyclic module out of the standard groupoid homology complex. So you can talk about HP of that. And you just have the usual term character, which goes to HP of the group algebra, and then project down to this group periodified
So
group.
I think in the so if you have a torsion-free group, I think you do have a churn character down to the group homology.
I think
I think
isn't this in the first paper by Down and Con? They do talk about the Chan character there. Maybe it's only for compact
might be
groups.
that. Yeah, I can't remember exactly where it's from. I'm sure that this is just from conversations I've had with people that like the group setting is known. And it might be so when you do have torsion in the group setting, you don't want to consider group homology. You want to consider something called Redon group homology with respect to the family of finite subgroups. So it's kind of so that it interacts with the torsion in the group in the same way that the K theory will, or in an analogous way. And I think you have a churn character in that context as well. Maybe this is sort of like Davis-Look stuff, I think. But I could be slightly wrong.
So say that again.
So you've got there's a homology theory for groups which agrees with group homology.
This whose name is this
Redon, I think.
sorry?
Redon? I mean, I don't know if I'm pronouncing the French. I think it's a French
No,
name.
no, it's okay. Yes. Okay, but you keep saying what you were saying, and I find the book.
Yeah. So there's this homology theory for groups, which I call Breton homology.
Breton. Yeah, Breton.
Yeah, exactly.
You said, is that a French name? I never thought, it never occurred.
I sort of assumed it was. I might just be making an assumption out of nothing because I don't think anyone's told me that it was. So maybe I'm just completely wrong.
I think he's American, I thought.
Oh, well, so the Breton, the Breton
Breton.
homology.
I mean, he might have some origin that's French. I don't know.
Yeah, I don't know. I've never known how to. Anyway, the Breton homology agrees with the homology when the group is torsion free, but otherwise it handles the torsion in a way that is better comparable to K theory, at least. And so I think you have some Davis-Look stuff, which is telling you have a Chern character in that context.
I mean, I know my Davis-Look well, but it never occurred to me that they should give a Chern character, but maybe it does.
I would have to. I could be wrong in saying that. There's the chance I'm misremembering something there, but I do think that there is a Chern. It might not be Davis-Look, but yeah.
Anyway, I mean, one way you can get a Chern character for groupoids or in any circumstance, under any circumstances, is you compute the cyclic homology. And then there is the Chern character, the Jones-Wiley Chern character. And that's it. Which is kind of what we are trying to do. But yeah, so, but then, I mean, depending on what the cyclic homology is, it might be more or less related to things you knew before, like the groupoid homology. But anyway, so I have a general question about independent resolutions. Namely, is there any, are there any of these things that one knows about projective resolutions of modules? Is there any of these true? Like, for example, if you have a resolution of length 10, then every resolution of higher length, you can already terminate it before, or, you know.
Yeah, I think these are great questions. I sort of, I want to understand what independent resolutions are these things where basically you want to resolve your groupoid by groupoids of this type, which not this type, but of this sort of type. The groupoids that look a bit like the universal groupoids of inverse semigroups, say, where you can actually compute the K theory and it splits up into this discrete thing. So they're definitely groupoids where you can actually compute things, at least relative to the isotropic groups. I don't have the feeling that they should no, I mean, the question is whether you can make them projective in some, or something like projective, whether you can endow them with some adjective from homological algebra.
Yeah, there is a notion of dimension. So, for example,
I want to understand more about that. Because it feels like there's some sort of triviality that's going on with these groupoids. some kind of freeness, some kind of, but it's I'm not sure. It'd be really nice to pin that down. Yeah.
Yeah. And also, since all this, so if you go the way of independent resolutions, then you abandon your groupoid and consider other groupoids, right? But these have something in common, namely, so if your groupoid is the groupoid of germs of some action of some semigroup on a space, then you change the place, but you keep the semigroup.
Okay,
and so, the reasonable thing would be the reasonable K-theoretic setting should be a semigroup equivariant K bivariant K theory, not groupoid equivariant, right?
Yes.
So yeah, so yeah, but I don't know if you see these things with in your setting that you I suppose when you look at the Bauncon with the left hand side that is some KK and but then there is this there is always some topology going on whereby you have some classifying space, right?
Yes.
Xing has this idea that there is this spectrum, blah, 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 which is fine. I mean, gives. But if I want to do repeat this for groupoids, and my groupoids and are ample, right? So the space is totally disconnected. And then if I look at spaces over it, especially if they are étale over it, they will also be totally disconnected, right?
Yes.
And so statements like space is unique up to homotopy, up to weak homotopy. The weak homotopy means an isomorphism at the level of homotopy groups. But the homotopy groups of a space that is totally disconnected are all trivial. Right? So when trying to figure out what the right version for Farrell-Jones should be, I ran into a problem that, well, first of all, the point has to be the space. So if you have a group, if you look at it from a single groupoid perspective, you have a space, which is the unit space. And so every G space is a space over the unit space. So the unit space is like the point for you.
Yeah.
And then you have to get a resolution of an equivariant resolution of the point with the stabilizers belonging to your favorite family of groups.
Yeah.
But, I mean, I'm thinking whether one should develop a homotopy theory for such things, or if there is another way. Because maybe, I'm sorry.
Yeah, I mean, what happens if you try to replace the sort of topological homotopy stuff with KK stuff, for example? Does that work better for totally disconnected spaces, or?
I don't know. So, for example, I mean, when you do Bauncon, you do have a space in the left-hand side. You have the sister algebras and space, right? Which is some specifying space. And I don't know. On the other hand, in the recent paper by Bartels and Luc, where they look at Farrell-Jones we prove a version of Farrell-Jones for Hecke algebras. They are very much like, I mean, they're similar to groupoid algebras in the sense that they are compactly supported continuous functions on a space that is totally disconnected and so on. But the statement they prove is about is in the same Davis-Loop setting. I mean, like they have a classifying space in a very traditional way. And yeah.
Right, yeah. Yeah, no, it's a good question. You mentioned something about wanting to think of morphisms. So you were thinking about, morphisms of groupoids where you probably have, different space but the same semigroup lying around.
Yeah. Well, that's another point of view where yeah.
I mean, that's
well,
what
you do have a point.
That's basically exactly what I was trying to do here, right? Is I have this one semigroup and it acts on two spaces. And I want to view this morphism, I have this sort of morphism I want to get between these two guys. And I did look to, there is someone who's developed a sort of KK theory for inverse semigroups, supposedly.
Yeah. But
I couldn't really make it work.
Tame Ivanov guy. I mean, there is this guy who keeps.
I think it's
using...
Burgstaller.
Burgstaller. Yeah.
Yeah.
No,
I couldn't.
Yeah,
it didn't seem right to me. It just basically
No.
seemed to be using. It was like sort of really just doing it with respect to a groupoid somewhere, which didn't feel like the right thing. In particular, if you were to make, maybe it is possible to make a good inverse semigroup equivariant KK theory. But one of my requirements personally would be that it includes this morphism here that gives you this map in K theory. Because I think it's a very natural thing. It should. I have this notion of. So when I gave this.
But if you have but as we discussed before, if you have algebra maps, if you allow stabilization, you are good with algebra maps, just for at least for the purpose of this particular map.
Yeah, I guess so.
But also, I mean,
no, but the point is about how do you encode the equivariance with respect to the inverse semigroup? Because what I've got here is I said that we could upgrade the topological correspondence into this correspondence of the groupoids. What's really going on is this topological correspondence is equivariant with respect to the inverse semigroup in a good enough way that you can do this. So I'd want to basically be able to encode that on the C-star level and work with those. I'd want to work with those kind of correspondences on the C-star level for my Kasparov cycles.
Yeah, well, I think of algebraic bivariant K theory, and there I already know that I have no hope of describing KK as some nice cycles. I have to use, have you familiar with these papers by Joachim Kunz, where he expands the domain of KK to more complicated algebras such as
I'm vaguely aware that he does this sort of thing.
Yeah, so the point is that you need this J conception. So you need to have a Yoneda theory in order to have excision. You need to have a Yoneda theory of extensions, of n-fold extensions, and this involves taking. So you have a universal extension which has a kernel, or you have an algebra A, you have a universal extension which has a kernel J of A. And then you need J to the n of A, J of J of J of A of A many times. And this is involved in the definition of when you construct KK, you need this J to the n. So it's awful, but it has a universal property, right? And if you, and even, I mean, my homotopy theory friends wouldn't even worry about any description, actual concrete description of KK. They localize, and then they get as a right universal property. End of the story. Yeah. Yeah. But but at any rate, I mean, so say you consider S spaces where S is the semigroup, and then the point that is the final object is this E hat, where E is the idempotence of the semigroup. At least, I mean,
probably.
Yeah, and but the problem of the total disconnectedness and blah blah blah, you still have
but this is the problem, right? Because I'm not sure the point is that space, because and this is the whole problem. Really, I want to divorce the inverse semigroup from the space. Like, because this doesn't fiber over this, right? In a natural way.
Yeah, you're right.
So that's exactly the problem I was having in trying to make this work. Like, this inverse semigroup, the inverse semigroup acts on these as spaces, and you can make sense of all of this, and they act on the C-star algebras and everything, but there doesn't seem to be, like, I can't think of a nice point for the.
Yeah, that's a good observation. But at any rate, well, to me, E hat, I mean, has the property that it really makes the space disappear, because when you take the transformation groupoid of S acting on it, you just get the group algebra, the semi-group algebra. So there is.
Yeah. And actually, I've just thought now, maybe. No, that's the wrong way.
I always wonder whether these independent resolutions somehow build a space, build a classifying space.
Yeah.
But
yeah, no idea. Like, can you somehow can you find a simplicial model for the resolution and then take a geometric realization of that?
Yeah, maybe something along those lines.
Yeah.
Yeah, but the spaces go one way, the algebras go the other.
No, but my thought was going to be maybe somehow you can try to fiber over a space, but instead of normal maps, you use some kind of correspondences. So
yeah,
and I think it's the wrong way around, though, because this is a correspondence from this guy to this guy, which is a bit like a backwards continuous map, right? Or like a forwards local homomorphism, but feels like what you want is more like a continuous map. And so, I mean, maybe you fiber everything over this guy. But yeah, I don't know. It gets, but fiber in the looser sense of having some kind of correspondence. I'm not sure.
Okay, so Euler public has run amok So let's begin by stopping the recording.